In this video, we solve problem number 6 from written homework number 6 from the spring 2021 semester in differential equations. We're asked to use the Laplace transformation to solve this initial value problem. So we always start by introducing our notation. We're looking for a function y of t. So we're going to let the Laplace transform of lowercase y of t, or little y of t, equal big Y of s. We always start that way because we like to introduce our notation. It's pretty standard that the Laplace transformation of a function of t would be denoted by a capital letter, the same variable but with a capital letter. But we don't want the reader to have to guess that. So we always start by telling them what y of s actually is. And then we take the Laplace transformation of both sides of the differential equation. So this is my notation for that. That's not standard notation. But the idea is I'll take the Laplace transform of this side and set it equal to the Laplace transform of that side. Now the Laplace transform is a linear operator. So that means we're going to have 2 times the Laplace transform of y double prime minus 3 times the Laplace transform of y prime minus 2 times the Laplace transform of y equals 10 times the Laplace transform of the Heaviside function at t minus 3. Well, we have a rule for the Laplace transform of a derivative. And it's this: under certain conditions, the Laplace transform of the nth derivative of f with respect to t, it's going to have n plus 1 terms. We're going to start with an s to the n. All the other terms have a negative 1 out front, and we have s to the 1 less power. So the powers of s will decrease. We'll have s to the n minus s to the n minus 1 minus s to the n minus 2, and so on until we have s to the 0 on that last term. Now, multiplying these s's is the Laplace transform of f of t, which we denote by capital F of s. Then we'll have f of 0, f prime of 0, and these are the original function evaluated at 0, and the order of the derivative increases. This last term is going to be a negative 1 times s to the 0, which we don't write, which is just 1, times the n minus 1th derivative of this, evaluated at 0. So if this is a third derivative, that's going to be the second derivative at 0. If this is the fifth derivative, that's going to be the fourth derivative at 0. But you're always going to have n plus 1 terms. So that is the rule that we'll be applying as we take the Laplace transform of this piece and the Laplace transform of this piece. So going back to the differential equation, we have 2 times the Laplace transform of y double prime. Matching this pattern, we're going to have an s squared times y of s minus s to the first times little y at 0 minus s to the 0, which is 1, times little y prime at 0. You want to make sure you keep all of that in parentheses because it's multiplied by that 2. That 2 has to distribute there. We have minus 3 times the Laplace transform of y prime. So that means n is equal to, well, n was equal to 2 there. N is equal to 1 here. So we're going to have 2 terms. And we start with an s to the first times y of s, and then we subtract little y evaluated at 0. And then we're going to subtract 2 times the Laplace transform of y, which we've denoted by y of s. And that equals 10 times the Laplace transform of the Heaviside function at t minus 3. Now, there are a couple of ways you could find that Laplace transform of the Heaviside function at t minus 3. I'm just going to go straight to my table, the table of Laplace transforms. This is from the ZIL Differential Equations textbook. And I'm going to look for the Heaviside function. They use a slightly different notation than we do. They use u of t minus 3. And I don't know if you can see it. It's right here on the list. It's number 51. Oops. Let me clear that. The Laplace transform of u of t minus a is e to the negative as divided by s. Okay, so we will have, well, first identify A. A is 3. So this is e to the negative 3s. And it's going to be multiplied by the Laplace transform of 1, which is 1 over s. If you don't remember that rule, that's okay. You can just look it up in the table, and it tells you that the Laplace transform of the Heaviside function at t minus a is e to the negative as over s. Okay, so this is the Laplace transform of our differential equation, but we still have these initial conditions in it. We want to substitute in our initial conditions now. We're told at the beginning that y of 0 is equal to 0, so we'll sub that in. And we're also told at the beginning that y prime of 0 is equal to 5, so we have that there. Okay, so we end up with 2 times the quantity s squared y of s minus s times 0, which is of course 0, minus 5 minus 3s times y of s minus 2y of s equals 10 over s times e to the negative 3s. Okay, now we're trying to get y by itself here. I want to solve for y, the Laplace transform of our solution. And to do that, I will distribute the 2. And then I will group all of the y of s terms and move any terms that do not involve y of s to the other side of the equation. So these guys all have a y of s in them. So that is 2s squared minus 3s minus 2 times y of s, and that equals this plus 10. I'm adding 10 to both sides. And of course, we can divide both sides by this in order to get y of s by itself. Now, it would be helpful if we could factor this first. You have some options for factoring. You can use factoring by grouping if you want to, or you can just think of it this way. I need my first times first to give me a 2s squared. So I'll have a 2s here and an s here. I need outer times outer plus inner times inner to give me a negative 3s. And last times last has to give me a negative 2. So we're going to have two numbers with opposite signs. They have to multiply to 2. So I'll have a negative 2 and a 1, or a negative 1 and a 2. And I need the sum of outer times outer and inner times inner to be negative 3s. I think I can make that happen if I put a negative 2 here and a 1 there, because 2s times negative 2 is going to be negative 4s, plus s is going to give me the negative 3s in the middle, and last times last is that. So we have this now. Now, if I want to get y of s by itself, I can divide both sides by this expression. But remember, dividing both sides by this is the same as multiplying by 1 over that. Remember, dividing by 2 is the same as multiplying by 1/2, right? So when I divide both sides by the quantity 2s plus 1 times the quantity 2s, or s minus 2, this is going to be a product in the denominator here and in the denominator over here. So I'll have 2s plus 1 times s minus 2 here, and then a 2s plus 1 times s minus 2 over there as well. And over here, we've got that. So we just have y of s, and that equals this, e to the negative 3s times 10 over s times 2s plus 1 times s minus 2, plus 10 over 2s plus 1 times s minus 2. So that is the Laplace transformation of our solution. It's called the Laplace transform. Now I want to take the inverse transformation in order to get y of t by itself. In order to do that, I need to remember this fact. It's also a rule from our table. The inverse transformation of e to the negative as times f of s is f of t minus a times h of t minus a. Now remember, f of t minus a is the inverse transform of f of s, that's going to be f of t, but then the t is replaced by t minus a. And this e to the negative as tells me we're going to multiply by a Heaviside function. So when I'm using this rule, I use it in the following way. I identify a, and then I know my formula is going to be this. Then I need to compute the inverse transformation of f of s, which is going to give me f of t. And then I substitute into this right-hand side. So we'll evaluate f at t minus a, and we'll multiply by the Heaviside function at t minus a. So that's the plan. In this case, this is our e to the negative as, and this is our f of s. So I have e to the negative 3s times 10 over s times 2s plus 1 times s minus 2. And I want to compute the inverse transform of that. It's going to be the first expression as part of my y of t. Well, if I'm pattern matching, and this is my e to the negative as, and this is my f of s, first thing I notice is that I've got a 3 multiplying my s there, and that has to be the a multiplying over here. So a must be 3. So according to our rule, we'll get f of t minus 3 times h of t minus 3, where f of t is the inverse transform of this. So we need to compute that now. Well, I don't have a rule for that, but I can rewrite that as a sum of expressions that I do have rules for using partial fraction decomposition. So I know that that expression can be written in this way, can be written as a constant over s plus a constant over 2s plus 1 plus a constant over s minus 2. And that's because each of these factors are linear and they're non-repeated. So I just need to find the values of a, b, and c that cause this expression to equal this expression. So we're writing the correct form of the partial fraction decomposition. We multiply by the denominator on both sides. The original denominator is the LCD. It's going to clear out all of our fractions. These guys reduce, these guys reduce, and these guys reduce. The s's reduce, the 2s plus 1s reduce, and the s minus 2s reduce. So what we end up with is this. We have 10 equals a times the quantity 2s plus 1 times s minus 2 plus b times s minus 2 plus c times s times 2s plus 1. And the easiest way to solve for a, b, and c is to just choose values for s that cause each of these factors to be 0. So this factor is 0 when s is equal to negative 1/2. So we substitute s equals negative 1/2 into both sides of the equation, but on this side we just have a 10. So we have a 10, no matter what s is, we get 10. And then if s is negative 1/2, we have negative 1/2 times 2 is negative 1, negative 1 plus 1 is 0. Since this factor is here, this is going to be 0 at s equals negative 1/2. And this factor is 0, so this term will disappear. So the only term that will not disappear is this one that doesn't have the 2s plus 1 in it. So we'll have b times s, which is negative 1/2, and then we have negative 1/2 minus 2, or negative 5/2. And if you want, you can multiply those together. You get b times 5 over 4, and that means that b equals 10 times 4 over 5. And of course, 5 goes into 10 twice, so we have b equals 8. All right, so that's b. Now choose a value of s that causes s minus 2 to equal 0. So let's try s equals 2. Then we'll still have 10 on the left-hand side. If s equals 2, we've got something times 0, so that's 0, plus something times 0, which is 0. And this does not have an s minus 2 factor. So if we substitute in s equals 2, we're going to get something non-zero over here. So if c times s, which is 2, times 2 times 2 is 4, plus 1 is 5. So we have 10 equals 10c, so c must equal 1. And then we will choose a value of s that makes this factor 0, which is just s equals 0. If s equals 0, this term is gone, and this term is gone, and we just end up with this one. So we have 10 on the left-hand side equals a times 1 times negative 2. So 10 equals negative 2a, so a equals negative 5. All right, so these are the a, b, and c that cause this expression to equal that expression. So f of t is the inverse transform of a over s, so it's negative 5 over s, plus b, which is 8 over 2s plus 1, plus c, which is 1 over s minus 2. Now, we have a rule for this and a rule for this, but the entries in our table do not have a 2 in front of that s. It's just an s minus a in the denominator. So to get rid of that 2, we'll just divide the numerator and denominator by 2. We'll get this. Divide that by 2, we get s. 1 divided by 2 is that 1/2. And then we're matching this pattern. The inverse transform of 1 over s minus a is e to the at. And the inverse transform of 1 over s is just 1. So this piece is going to be negative 5. You could factor out the 5 if you wanted to. You'd call it negative 5 times 1 over s. And then we'd have a 4, bring that down, times 1 over s plus 1/2. In this case, a is equal to negative 1/2. So we'll have 4 times e to the negative 1/2 times t. And then the last one is a over, or 1 over s minus 2. The inverse transform is e to the at. A is 2 here, so we'll have e to the 2t. That's our f of t. Okay, but the inverse transform of this piece is f of t minus 3 times h of t minus 3. So that means the inverse transform, of e to the negative as times that f of s, which we rewrote using partial fraction decomposition as this. This is a 3. Is equal to f of t minus 3 times h of t minus 3. And f of t is right here. So we'll replace the t's with t minus 3's. We have negative 5 plus 4 times e to the negative 1/2 t, but t is replaced by t minus 3. We've got that there as well. Okay, so that's for the first piece. That's for this piece. This piece, we also have to use partial fractions, and then we'll add those together, and that's going to be the inverse transform of y of s, which is y of t. Okay, so for the second one, we've got 10 over 2s plus 1 times s minus 2. That's equal to a over 2s plus 1 plus b over s minus 2. And we'll multiply by the LCD, which is 2s plus 1 times s minus 2. So we state the form of the partial fraction decomposition. And then we do this. These guys reduce, we just get a 10 equals this. It's a times s minus 2 plus b times, these guys reduce, the quantity 2s plus 1. So we let s equal 2, that'll make this 0. So we'll have 10 equals b times, 2 times 2 is 4, 4 plus 1 is 5. So b is equal to 10 divided by 5, which is 2. Or if s equals -1/2, that's the value of s that would cause this to be 0. We have 10 equals a times -1/2 minus 2. That's -1/2 minus 4 halves. That's -5 halves. So a is 10 times -2/5. 5 goes into 10 twice, so we get -4 for a. So our y of s is e to the -3s times this plus the partial fraction decomposition of this, which was a over 2s plus 1, so -4 over 2s plus 1, plus b over s minus 2. And we want this to be a 1, so we'll divide the numerator and denominator by 2 to make that a 1, so that it matches the form in our table. So we can say minus 2 over s plus 1/2 plus 2 over s minus 2. And we'll take the inverse transform of this whole thing to get little y of t back. So this first piece we've already done. It was -5 plus 4. Oops, I forgot earlier. It's all of this times the Heaviside function at t minus 3. There we go. Sorry about that. Plus the inverse transform of this piece, which is -2 times, this is 1 over s minus a, where a is equal to -1/2. We get e to the at, so we'll have e to the -1/2 t. Bring the 2 down here. The inverse transform of 1 over s minus 2 is e to the 2t. So that is our answer, but typically we like to write it in terms of, or as a piecewise function, rather than in terms of the Heaviside function. Now remember, the Heaviside function is 0 until we get to 3. And then at 3, it jumps up to 1. That's for the Heaviside function at t minus 3. This number tells you when that sort of on-off switch turns on. So it's 0 until you get to that point, and then after that it's 1. So when I write my y of t, it's going to be a piecewise function with 2 intervals, one on the interval from 0 to 3, where the Heaviside function is 0, and another one on the interval from 3 to infinity. Well, when the Heaviside function is 0, we get this times 0 plus this. And then on the interval from 3 to infinity, this is a 1. So we have this times 1 plus this. So we'll have -5 plus 4 times this exponential plus that exponential plus those 2 exponentials, and I'm sort of running out of space, so I'll factor out the 2 to save space. And that's on the interval from 3 to infinity. So we had to use this inverse transform of e to the -as times f of s rule, which is, well, first we have to find the inverse transform of f of s. It's going to give us f of t, but then we replace the t's with t minus a's, and then we multiply that by the Heaviside function at t minus a. So that gives us f of t minus a times h of t minus a. And we had to do a little bit of partial fraction decomposition in order to get this into the right form. We had to do it twice. But the beginning is pretty simple. We always start by letting the Laplace transform of little y equal big Y. Take the Laplace transform of both sides of the equation using this rule for the Laplace transform of the derivative. Substitute in your initial conditions. Then you've got y of s, or then you've got an equation involving y of s. Solve for y of s. You end up here. And then we do the necessary algebra to write this in a form so that we can take the inverse transform. So it requires partial fractions here, then finding the inverse transform of this piece, which gives us f of t, And then we replace the t's with t minus a's and multiply by a Heaviside function at t minus 3 because a equals 3. And then this is just sort of traditional, but you got to do a little partial fractions first so that it looks like our e to the at inverse, or it looks like the function that we would take the inverse transform of to get an e to the at. And then finally, after you do all of that, it's a good practice to write your final answer as a piecewise function rather than writing it in terms of the Heaviside function. Because when people think about functions, they don't often think in terms of the Heaviside function. They think of functions like this. So it's nice to give our reader a form of the solution that they're comfortable with, and this piecewise form is a form that most people are comfortable with.